Welcome, this is the AP Physics video lecture. This is covering dynamics. The topic is centripetal force. Now we're going to look at the normal force. To motivate today's lesson, I would like to show you a video clip. Here, this is a ride in the carnival. You might see this as the gravitron or the rotor question. Here, students or people are placed on the side of this ride and the ride will spin circularly. Notice that it's starting to pick up speed, so there is a tangential velocity that is increasing. Notice as it's increasing, that floor, which is red, is now going to drop. Right here, the floor is starting to drop, but notice none of the students here fall down. Notice that the students here are pushed up against the wall completely. The students are not going up or down, but is completely up against the surface of the ride. So the example here, we're going to call this the gravitron here, is a common amusement park ride where the room spins so fast that the occupant feels pressed up against the wall, like the video that we saw. When significant speed is reached, the floor drops, but the occupants do not slide down the wall. Let mu become 0.7 and the ride radius is 2.5 meters. Part A. Complete the free body diagram for the riders in the position shown. There's a force gravity that's pulling them down, and there's actually a friction going up. The force normal is going towards the center of the circle. It might make sense because this is from the side view, and if I draw it from the top view, it looks like this. From the top view, you only see the force normal. Here's the person, and goes towards the center, and that is the normal force here. So, the first question. What is holding the rider in, keeping him from shooting out of the room? That would be the normal force. The normal force is pointing towards the center. Right? We know that this object is spinning, so there has to be a centripetal acceleration. So what force here is supplying the centripetal force? Here it would be the normal force. What is keeping him from sliding down the wall? In this case, the equal and opposite force of Fg is F, which is going up, force of friction. But this leads us to the bigger question. Why is the force of friction upwards in this situation? There are two answers. One, the friction force is perpendicular to the normal force. Or you can think about the force keeps you from sliding down the wall is the static friction force. It must point up because it has to balance the gravitational force that points downwards. B. You're going to compute one equation to describe the force in the vertical direction and one equation to describe it in the horizontal direction. The summation of the forces in the y direction is friction minus Fg, because I'm taking down to be negative. And the summation of the force in the x direction, which is the horizontal direction, was just the force normal. So what direction is the centripetal force in? And is there even one? We know that the centripetal force, so the summation of Fc is equal to n. We can make that substitution. The summation of Fc is equal to mass times velocity squared over r. Explain what happens to the normal force as velocity increases. So V goes up. If V goes up, the normal force will go up because they are directly proportional. V is on top of the fraction. What happens to the force of friction as the velocity increases though? Well, we know that if velocity increases, the normal force will increase. Velocity increase will increase the normal force. Okay, we saw this in part 2 of the question right here. If the force of friction will increase as a result because F is equal to mu n. And we saw that the normal force has a direct relationship with the friction force. And we saw that the normal force here will increase. The normal force increase, the force of friction will also increase. Okay, so think about as the ride spins faster and faster and faster, the person is pressed up against the wall more and more and more. And then the molecules are locked more, so that's why the force of friction increased. Now you have these values, mu equals to 0.7 and the ride radius is 2.5. You could actually compute the minimum velocity that is required to keep the person from not falling to gravity. So we should see the summation of the forces in the ride direction equals to F minus Fg. And we know that the force in the x direction is the normal force. The person does not fall down or go up. So we set that equal to 0. It's in equilibrium in the vertical. So it balances out. The force of gravity is equal to the force G. We can plug this in. Okay. Force of friction is mu n and Fg equals to mg, right? We're on Earth. Okay. Force of gravity, mg. But you need to know what n is. We could get n from the summation of the F in the x direction. So make that substitution. mv squared over r equals to the normal force. Now we plug it in. Once we plug it in, we can solve for v squared. V squared is equal to gr over mu. Take the square root, plug in the values, and you see it as 5.9 meters per second. This is the minimum speed required to prevent the person from slipping. Something interesting happens, and I want you to look at it. Does mass matter? Does the person mass affect the required velocity to make the person be up against the wall? So a fat person, a skinny person, does that really matter? If you look at the equation, mass cancels out. So no, it doesn't matter. This should remind you of our previous problem during the entire unit. Why does the object's mass not matter when it comes to tangential velocity and the centripetal force? All three of these problems, you see how mass cancels. The first one, revolving a ball in the vertical direction, we spin it, and we saw that the minimum speed at the top equals to this. Notice mass cancels here. So the final answer was v equals to the square root of gr. Even when we did the planet one, we see that the speed of the planet does not depend on its own mass. Okay, so the mass cancels here. So this one would be v equals to the square root g m(e), mass of Earth, over r. And lastly, we talk about an object going around in a circle. So there's a normal force. The velocity at the top for it to barely make it over the top is square root g over r, right? Exactly like the minimum speed at the top here, right? Notice all these are mass independent. Mass does not affect the velocity whatsoever. Lastly, I want you to think about this idea of artificial gravity. So here's the situation. Jake is the director of NASA and is tasked on designing a next generation space station. One big problem in space is that the astronaut's muscles and body will break down if there isn't any gravity, and as a result, no way to work out and stay in shape. Using what you know about centripetal acceleration, draw and design a space station and describe in a coherent paragraph how it works to fix this issue of gravity. Take this time to do that. Here we have a picture of a space station in a movie called The Martian. Here, these are tubes and it spins. So it looks like this. It's like a circle and it spins. So there's a tangential velocity. The space station has a circular motion with constant velocity. It spins. The fact that it spins, right, the v changes direction, so there has to be a centripetal acceleration pointing towards the center. The change in velocity direction creates a centripetal acceleration, and as a result, a centripetal force arises. Due to Newton's third law, every force has an equal and opposite force. And that equal and opposite force is going to be the Fg. The force of gravity is created as an equal and opposite force to the Fc due to Newton's third law. Here, you just created gravity. The gravity came from the space station rotating, creating a centripetal acceleration. Then, as a result, due to Newton's third law, gravity is now created. This is how you make gravity in space. All right, there you go. That is everything that you need to know in regards to centripetal force with the normal force in it.